So I'm going to be talking about recovering a functional and three-dimensional understanding of images. And I'll sort of tell you what I mean by this by sort of giving you an illustration of your amazing ability to do vision yourself. So all of you are already experts in vision. Simply by walking around for however many years, you've actually become very good at this. And so I like beginning my talks with an illustration of how much you actually know. And so here we have a picture that I think most of you have not seen before. And certainly none of you have actually been to this place. And despite this, you actually have a very good understanding of what's actually going on here. And I like actually doing this as an example. And I'd like each of you to actually think about what would happen if the man behind the counter gets milk from the fridge. Just like think for a few seconds. So I hope all of you can actually imagine this, and it's really actually a quite simple task. But let's just go through it together to make sure everyone's awake, because it's before noon, and we know with academics often their brains don't turn on until afternoon. So here we have the man behind the counter, and you have the fridge in the back, and the man's going to have to walk over there. Pretty straightforward, right? When he gets to the refrigerator, and then we're going to see whether the video works, since this is on a Mac now, he's going to reach out, and he's going to grab the refrigerator and open up, and then take the milk out of the refrigerator. And so this is an incredibly boring hypothetical example, and I hope it's the most boring example that you've seen someone give in a talk for at least the past few years. But it's actually kind of amazing, and it's worth thinking about why it's amazing. And it's amazing because if you look at this image, and you actually think about what's in this image, well, there's actually just a collection of 2D intensity values. And there's nothing more and nothing less. And yet, from this collection of 2D intensity values, you're able to extract some sort of understanding that lets you reason about how people can move around in this scene, what they can do, how they would interact with stuff. And you're able to do this, and this is an example which I think is completely non-controversial. And it's something that you can do. It's something that a 3-year-old can do, and it's something that I'd expect that your household pets like a cat or a dog would understand at some level. And so what my sort of group works on, and what I've been sort of fascinated with for many years, is taking an image and extracting from it some sort of 3D representation of it, in the sense that I know that there's the man behind the counter. I can see the floor. I can see that there's a floor behind the counter. I can reason about space that I can't even see. And then, so this is 3D. And then in terms of functions, it's that I can reason about how everything in the scene functions. So in the same way, like toddlers like opening things and closing things and throwing things on the floor and doing all sorts of stuff and causing havoc, I'd love to have a system that understands how can I cause the most havoc in this kitchen? What can I knock over? What can I open? How do I throw everything on the floor? And I'd like to have a system that has that level of understanding that lets it do things very efficiently and understand how things will happen. And so I'm going to be talking about these 2 lines of work today, showing some work. So I just started, so there's some work from before I started, and then there's some previews of what's coming, hopefully by the CVPR deadline. And so I'm going to begin by talking about how do we perceive an intrinsically 3D world from a 2D image. And so, for example, we have, there are lots of systems that can produce 3D results. And so, if you have an autonomous vehicle, you're going to be equipping it with LiDAR. And so here, for example, on the left is an image of some scene. And on the right is the output of a very nice, actually, laser scanner. And so this is actually a very nice one. It's about $50,000. And it takes about 6.5 minutes an image. So on the right, I'm showing the orientation of the surfaces. And so this was actually, the laser scanner is so good that you can use the world's worst algorithm for figuring out the orientation, and it actually works, and you actually get beautiful. You can see the little leaves on the plants if you look at it in high def. And so this is great. So this is a really expensive, wonderful piece of equipment, and people collected data like this. And so you might say, aha, well, to get a 3D understanding, we just need to get a bunch of sensors, point lasers at stuff, and then we're done. But let's ask some questions that you understand, your 3-year-old understands, and your cat understands. So for example, let's look at this table. How thick is this table? What's behind it? Is the chair attached to the table? And these are really basic questions that all of you understand, but they're actually not even accessible in some sort of laser scan map of the thing. And so what I've been interested in for many years has been 3D, and I've become especially interested in 3D construed very broadly. Like how does a physical world work in terms of there are distinct objects, they can be moved around, and there are things that I can partially see. And so one of the things I've been working on has been producing 3D reconstructions of scenes from images. And so we can take, for example, an RGB image, and one of the outputs that we have been producing has been voxels. And so if you are some of the younger members of the audience, you probably have played Minecraft, and if you're one of the older members, maybe your children play Minecraft, and you're tired of watching them play Minecraft or watch YouTube videos of it. And so, but a voxel is simply just the Minecraft representation of the world. So we can take this image, and what we might do is we might try to represent it in terms of whether things are on or occupied, or off and empty. And so, for example, we'd like to be able to take this chair and produce a reconstruction like this. And so this would rotate, and the point of the rotation, and the reason why I would stick a video in, which Mac is not liking, is that the point is that we can reconstruct not only the legs that we can see, but also the legs we can't see. And so, of course, this is under constrained, but what we're going to do is we're going to make our best guess. And so the systems that we use, and so I'm going to be primarily just giving you a flavor of what we do. But to give you a sense of what's going on internally, the systems tend to consist of, you have an input image, and of course it's deep networks. And so you have two-dimensional convolutions which operate on the image, and they go to some sort of representation. And this is some sort of latent feature space of shapes. And this thing, essentially, some dimension represents to what extent, how many legs does it have, how thick they are. And of course, there's lots of reading the tea leaves in terms of figuring out what the dimensions represent. And of course, it's also very difficult to actually really know what's actually going on here. But you take this feature space, and then there are three-dimensional convolutions that actually produce a final voxel map that produces a sort of like Minecraft representation of a chair. And so we've been training these systems on primarily synthetic data. And so I'm not going to show you the testing on that, because that's kind of boring. And of course, it works if you train and test on synthetic. But what we can do is we can test on Ikea furniture. And just as Justin was training and testing with Ikea furniture, it's wonderful. They make the stuff. People take pictures of it, and they show off the fact that they successfully assembled it. And so they're really proud, and they tag it, and it's great for collecting data. So here we have a bunch of furniture, and you might be able to spot some of the stuff you have. So in fact, this thing I had through grad school, and I liked it so much I got it as a postdoc for like $9.99. And so on the right is our output, and so it's represented in terms of its probabilistic thing. So the red stuff we're really confident about and we're sure is there. And there's little bits of dust floating around, and these are things that we're less confident about. So you can see that the system does a reasonable job. So this is actually from the data set's from 2013. Our method is from 2016, when this first started becoming really feasible. And of course, one thing that I always try to emphasize these days in AI, because it is, in fact, in some sense, the best of times, stuff starts to work. One thing I always want to emphasize is it's not magic. You can't just magically put things in and stuff comes out, it's all great. So for example, bookshelves we didn't train on. And so we stick it into the network, and it tries to reconstruct it as some sort of very weird table, and there's a hole in your bookshelf. So it's, there are lots of things, there's a long way to go, and it's also important to remember that the data that we're using is actually very important, and there are lots of profound issues that you can have if you go and you try and you extrapolate on new data. So this is with a single object, and so we've been trying to push this to the limit. So one thing we're doing is we're trying to do entire scenes. So I can take an image, and so I can have a collection of boxes, and so this is provided by some other system. And if you've seen detection, it's very much like this. And so we can take the boxes, and what we do is we have a convolutional network, and we kind of look at the features inside the convolutional network at the box. And we have a system that can produce, for a single object, it can produce the voxels. And so this is just like reconstructing the Minecraft representation. But it also produces a scale, a translation, and a rotation. So you can imagine this is kind of like making a CAD model of your scene. So it's a network that outputs all these things. And so this entire thing is trained end to end. Of course, right now we depend on enormous amounts of supervision for this. And so it's trained by synthetic images. But what we can do is we can actually transfer this to real world stuff. And so here we have images from this data set called NYU. And here's the output from a system. And here it is rotated from another view. And so I started working on 3D computer vision in 2011. Back in those days, we would never, ever, ever rotate any of our results because they all look terrible. And now we can actually rotate them, and we can now see charming failure modes and lots of new exciting things to fix. But what's fun is I'm going to zoom in on one of these. What's fun is you can see that here we have an image, and it's rotated. And it's not perfect, but it gets the TV on the left. You can see that it's getting a bit of the table further into the room, and it's doing a pretty reasonable job at reconstructing stuff. And so that's kind of exciting. OK, so some ongoing stuff that we're doing. Some of my students are hard at work right now trying to extend this to multiple views when we have sparse ones. OK, so we can make these systems, and they can reproduce sort of the 3D structure of the world. And the cool thing is because it's broken into objects, we can do things like if I don't like this table, I get rid of it. Because it's 3D, if I want to see it from another view, I can rotate it. And because the objects are separated out, I can actually do something like, for example, pull out the chair from underneath of it. So the representation has factored everything into objects. Now, one question you might have is how on earth do you know that you can pull the chair out from the table? And so this gets to the sort of other thing I'm interested in, which is how can we have humans and I hope eventually robots interact with things. And so I'm primarily now watching how humans do things, and I'm hoping to apply to robotics eventually. So here we have a kitchen, and here's one answer that I've been working on for a while. If you want to know what we can do in this kitchen, we simply watch what this woman is going to do. And so what we can imagine is we can have systems that watch enormous amounts of video data and that learn about how the world works and how do I operate things and how do I manipulate things. And so one of the things I did before I came here is I gathered a large-scale data set, which is called Vlog, and it's from lifestyle vloggers on YouTube. And so it's 14 days of the world's most boring footage. This is dreadfully boring, just so unbelievably boring. And if you watch what people do, you can actually learn models and build models of how people do things like move their hands through scenes and what they do and how they pick things up. So here we have an image, and so you can predict what will happen in the next n frames. So we have 2 frames, 8, 16, and 32. And so actually there's a lot of lifestyle vlogging videos show a lot of, for example, facial products. And so this is actually, it's learned this very well. For example, people like to show that they make their beds because they've got it together, and so they always make their bed in the morning. 2 frames, 8 frames, 16, and 32. So this learns it. The one which is really depressing is this one. So we have someone using their phone, and we've all been there at lunch with someone who's using their phone. And I'm sure you can guess where this is going. 2 frames, 8 frames, 16 frames, 32 frames. So it's a bit depressing what you learn from watching people, and I'm not sure we want to have these demonstrations. So we have this system. It's 14 days and the most boring footage, and so I'm trying to extend it now further. And so one of the things that we're working on right now, and we'll be submitting to CVPR, is a new data set called 100 Days of Hands. So it's about 131 days of YouTube video. So why is it called 100 Days of Hands? Well, it sounds better, and it's kind of fun to have other people's data set sizes be in our round-off error. And so it's lots of people doing their hands to do lots of things. So one of the things that was weird about Vlog is it's this lifestyle vlogging stuff, and it's a very, very weird set of data. And so we now have a much broader set of videos. It's not perfect, and so I'm continuously trying to get better and better videos, but it's a bit hard because you have to find something on YouTube that actually happens. And we have a new data set, and so this is joint work with my students Dan Dunshan, a visitor from Johns Hopkins, Michelle Xu, and a Michigan undergrad, Jiaji Geng. And we have a data set which is now, have about 100,000 images, and we have these frames of this video is annotated, and so there's about 189,000 hands that are annotated with a hand bounding box, whether it's a left hand or a right hand, which, as if you've done this, you see people who are over 20 doing this thing where they look at the left hand, makes an L. This is actually a bit difficult, and it's difficult for machines to do. Whether the hand is in contact with stuff, and also what it's touching, and so what objects the hand is in contact with. And so I have a video which will not play, but I promise you that the results are wonderful, and you can see just 1 frame. And so we're able to detect hands with actually surprisingly good accuracy. And so what we can do is we can then detect the hands and the objects. And so one of the things that I wanted to do is in order to watch how people manipulate objects, we really need basic tools to be able to extract this information. And so what I said is I just want a hand detector that just works on all the data I can find. And so what we did is we went out and we made one. And so the accuracy is if you do object detection, the accuracy is around 90% AP. So this is actually, we're looking for failures as opposed to looking for successes, which is quite nice. And so we can track the hands and the objects, and it's not playing. But one of the things that the system lets us do is because we can get where the hands are, and we can identify their contact state, whether they're a left hand or a right hand, and we can do this really reliably. We can start deploying stuff that people have used in the lab and actually get it to work in the wild data. And so one thing that our system enables us to do is apply existing machinery that people have developed and just apply to large amounts of data. So here's a system which is from some of my collaborators at INRIA, which essentially reconstructs the mesh of the hand. And so because our system is able to reliably detect hands and also their state, and also there's a system which can determine whether the mesh system works or not, we can generate enormous amounts of large-scale just hands doing stuff. And so now we have, you can imagine, we have 131 days. And so this is essentially basically like a year, because if almost a year's worth of footage, because of course it's actually 24 hours. It's not you can't actually watch this footage for 24 hours straight. And so we can actually extract lots of information about this. And so I'd like to conclude briefly with sort of a sense of where the sort of future is going. So the stuff I've been doing, and this is primarily stuff that has happened before I joined, and this is a little bit of where it's going with Michigan. And so what my lab is working on is trying to learn about the physical world by watching raw video data. And so the hope is that we can have systems that can ingest enormous amounts of videos and figure out, for example, how does these objects work? How are objects separated from each other? How do I manipulate things? How do I pick things up? What can I do here? And the hope is to be able to produce large numbers of systems that can actually learn from enormous amounts of data. And then eventually, I hope, in collaboration with the wonderful robotics people here, apply this stuff and actually get robots to really do things in the real world. Thanks.
Questions?
Yeah.
Is there work on generating these types of actions from scene understanding, like basically generating those human hand actions and all that kind of stuff?
Yeah, so there's definitely a lot of work. So we are simply watching the videos, and there's a lot of wonderful work in the robotics community that I'd like to connect with. And so the hope is that some of these techniques for generating hand actions, we can apply them, we can essentially provide training data for them. Now, one thing that's also very interesting is that in robotics, you do not have a wonderful hand like your human hand. And so this big question of how do we actually go from like demonstrations of human hands to actually how a robot hand would actually be able to do that, like a parallel jaw gripper. And so that's work that I'm looking forward to collaborating with the wonderful people here on. But right now, we're simply just trying to get the data so we can learn how just a human would do it.
Okay, just in case. Okay. So I would have thought that active control as part of this perception could add something. Do you think it would? Or do you think you can do all of what you want to do with just passively watching things?
Yeah, this question of how much active control do you need is actually like the question I want to know the answer to. Like if I could fast forward 20 years and find out what the answer is, I'd love to find out. Certainly active stuff makes things go much faster because you can try stuff, you can do experiments. The reason why I'm now very interested in this passive stuff is because you can scale it up in a way that right now we can't actually get active stuff to do. So you can get enormous amounts of data that just happens to be there. And I think the true solution will imagine combining both, but I think it will require some amount of active stuff in order to actually do it. But I think there's an enormous amount of stuff you can get out of simply doing passive stuff. And it can certainly make the active stuff even go faster, because if for example, you look at how do you manipulate this, you can try by flailing your arms around and trying a bunch of things, or you can simply watch one person give you a demonstration. And then you have a much better initialization for how do you actually actively control. But I think this is a fascinating question of where actually between fully passive and fully active do you go.
Volumetric image from a chest radiograph?
So yeah, this generating CT stuff. I've not worked in. I'm actually starting to work in medical imaging, but certainly not in that more of a discriminative as opposed to generative process. So I don't see why the techniques couldn't be used to try to generate a volumetric CT scan. Although I think it would kind of be just one of these examples of you get a bunch of inputs, you get a bunch of outputs, you train a deep network, plug your ears and hope for the best. So I don't have any very good thoughts on how you do that.
Great, thank you so much, David.